Hello YouTube! So today we're going to be talking about the difference between averages and instantaneous values. And in particular, really all the vocab words from last time, but now average versus instantaneous. So pretty much it's still just describing how stuff's moving. We're actually going to start with some numbers. Nothing too intense, but we are going to do some numbers. So get ready for that. And the big one is that if you can explain and really understand the difference between when you say that something's average, speed, acceleration, velocity, any of those things, is a value, how that's different from if you say that it's instantaneous speed, velocity, or acceleration are a given value. The other big one is thinking about which of those things we've talked about so far are vectors, which of them are scalars, and then also being able to find the magnitude of a vector, which is incredibly easy in one dimension. But it is still this sort of extra step vocab word that can throw people off. So, what's a vector? What's a scalar? Well, basically, sometimes the direction of something matters. If I say go 20 feet, you're not necessarily going to know where you're supposed to wind up or which way you're supposed to go. And so me saying go 20 feet forward, very different from 20 feet backwards. So the way we represent that direction is with an arrow. Basically, you got to point it the direction, right? Or you can use it with words, but when you then go to do math with it, or when you then go to draw it or something like that, that'll be using an arrow. These arrows are called vectors. So scalars are stuff you're used to. So this would be something like saying I have 6 apples, or 20 feet, just 20 feet tall maybe. These aren't telling you a specific direction. You could measure that 20 feet tall from the top to the bottom or the bottom to the top. They're just sort of saying, here's a size of a thing. Here's something to represent how much of it there is. And vectors are really close to that, but they're these arrows that also tell you which way it's going. It's not just 20 feet, it's 20 feet north, 20 feet south, something like that. And so that's really the only big difference between the two. There do wind up being a lot of repercussions from that, from like a math perspective. But as far as a conceptual perspective goes, scalars are just telling you how big something is. Vectors are saying this is how big it is, and this is which way it's going. You might have noticed that vectors contain what a scalar does. This is called the magnitude of the vector. So when I said 20 feet north, 20 feet, that thing that tells you the size of it, is a scalar, and it's the magnitude of the vector. So all you have to do to get the magnitude of something, if you know what the vector is just not give the direction anymore. And as soon as you do that, it's become a magnitude. This is actually represented by the absolute value symbol. So if you see something in the book, it'll be in bold. If you see something like this, the arrow on top means that it's a vector. This is me writing V in a kind of weird way just to make it different from you. And the absolute value symbol on either side means the magnitude of that vector, or literally just take the number. Because the math that you can do with vectors is actually pretty different from the math you can do with scalars. So sometimes it's really important that you convert your vector into a scalar, basically. And the way you do that is by finding the magnitude. We're really only living in 1D for this unit, which means that forward is positive, backwards is negative. You don't have to make that be the case, but for most of what we're doing, that's going to be the case. So because moving 20 meters backwards is a greater distance moved than 10 meters forwards, really, really relevant that you don't think of negative as small. This is something that is true for math class, and when you're dealing with like scalar math, having a negative quantity is different from having a backwards arrow. For vectors, that backwardsness doesn't determine the size and is completely separate. So just be aware that when you have something that's getting more negative, that doesn't necessarily mean it's getting smaller. This really throws people off for graphs. So far, we've actually talked about 3 vectors already. There were 3 things we talked about that had a way you could point while talking about them. The 3 ones are So velocity, position, and acceleration. So we'll get into a little more detail on these. So when we're talking about velocity versus speed, remember that speed is talking about how far you go, and velocity is talking not about how far you go, it's talking about how far you move and in what direction. So it's kind of describing on a second by second basis. You go from here to here, then here to here, then here to here. And so total distance traveled is a scalar that represents what you, the way that you did something, but you don't actually know what you did when you did it. Similarly, speed is telling you about how far you're going each second, and it describes how you're moving, but it doesn't tell you what's actually happening as a result of that or where you wind up as a result of that. Whereas displacement is telling you where you go. Specifically, it's this vector that describes like you started here, you end here. And velocity is telling you where you're actually going and how fast you're going there. So velocity is also this vector that predicts the results of the motion you're taking. And so when we wind up describing these, total distance traveled is really closely related to speed. Displacement is really closely related to velocity. We're going to start talking about averages because this is something that's really useful for modeling. And basically, averages is a way to take a complicated problem and make it easier. So for what most people are used to, they're like, well, if you want to find the average of a bunch of numbers, you just add them together and divide by how many numbers there were. And that'll work for some things. But if you're really doing it or really thinking about it right, and by right, I mean the way that we do in this class, what an average is something that is a uniform, meaning the same value that creates the same end results with the same number of things. So if I were to talk about the average height of the people watching this video, what that average height would represent is if I wanted to take everyone and have them stand on each other's shoulders, how could I get the same number of people who were all the exact same height to stand on each other's shoulders and make the same tower? And that's really what we're getting at an average. How do you get the same end result using the same amount of stuff? That last bit's going to become really important for when we're thinking about average speed and average velocity and how to find them and what they actually mean. So when you're talking about instantaneous speed, that instantaneous part, you can hopefully see the word instant is embedded within it. What that means is it's happening right now. So when you're saying the instantaneous speed, that's describing the speed the thing is going at immediately right now. Whereas if you're talking about average speed, you're saying, well, I mean, looking at what happened, it was basically like it was going at this speed. And what that means is it's the speed that would have had the same distance going under your feet in the same amount of time. Not necessarily bringing you to the same place, but definitely making it so that if you had to only go one speed the whole time and get the same end result of ground going under your feet, that's what would do it. And because of that, it needs to track what ground is going under your feet, which is your total distance traveled, right? And so that's the one that it winds up using. Whereas your instantaneous velocity, again, we see that instant in it, meaning like right now, is talking about not just how fast you're moving, it's also talking about what direction you're moving in. Something that's going to become really important about this eventually is that this is always a straight line. Instantaneous speed says absolutely nothing about it being a straight line. It doesn't say anything about how you're moving at all. Instantaneous velocity is saying if nothing changes, you'll go in this direction at this speed. And this is what you are doing right now is such that if nothing changed, you would go from here to here in a second. Slightly different because it's not just how fast you're moving, it's also saying what direction you're going in, and that introduces the line part of it. Average velocity is a little bit different from average speed, because instead of average speed describing roughly how fast you would have to go to do the same thing, average velocity is saying if you wanted to get the same end result, which direction should you go in and how fast should you go so that you only went in a straight line from point A to point B without changing what you were doing at all the whole time. And so it's the uniform speed and uniform direction of travel, meaning that the speed doesn't change the whole time, the direction doesn't change the whole time, that brings you to the same place compared to where you started from in the same amount of time. And that one uses displacement. As far as 1D is concerned, unless you're turning around, these are basically the same as each other. This gets a lot more different when you have turning involved, though. I do want to say really quickly, this is the end of the slides. I do want to say, I think we'll get into the math of this next time. And if we don't, I will make a new slide and we'll do another video. I do want to add that acceleration is also a vector. You can accelerate forward, you can accelerate backwards, and what that does is actually really going to change based on what it is. The direction of velocity tells you which way you're moving. The direction of position tells you whether or not you're in front of something or behind something. The direction of acceleration tells you if you wait an infinitely long amount of time, which way you will wind up going. But it mostly tells you, like, this is what you're adding to your velocity. So if it's backwards, it's saying, well, you add backward stuff to your velocity. If it's forward, it's saying you add forward stuff to your velocity. And what the object does is actually going to be really heavily dependent on what the object is currently doing, which is kind of a weird way to think about it, and it's a little counterintuitive, but because of how the underlying things that cause motion and cause motion to change work, really important that you're thinking about it that way, especially for when we get to the forces unit. So that's it. Goodbye, YouTube.